Okay, so it's 9 o'clock. I guess I can go ahead and get going. There will probably be a few more people trickling in, but no harm in getting started now. So my name is David Mertens. I am one of the core hackers on PDL, and I started working with PDL probably 5 or 6 years ago. And my first foray into it was I had just finished the Camel book, and then I was playing with something, and they messed with $_ in some of the code of PDL, and I discovered it in some weird, obscure edge case. And so then I'm like, oh, this is easy to fix. I'll just localize where you assign to it. And that was what got me into working with PDL, like the core. And I've been hacking on a number of things at different times. I won't be going into hardly any of that material. This is going to be an introduction. So the goal for this, maybe the first 20, 30 minutes, is going to be like going through a bunch of different calculations you can do and showing you how to do things. And then I'm going to kind of change gears and show you a bunch of resources online and whatnot to learn more. And then if I have time, I'll go through a real-world set of calculations I did. Unfortunately, I don't have my coolest work from work, but I do have some analysis I did for my mom, who's diabetic, and so I analyzed her blood glucose data. And it gives you just a basic idea of some of the analyses you can do. So I'm curious about a show of hands. Who here actually uses PDL currently? Wow. Okay, so all of you are new. Who here has tried to read the documentation on it? Okay, good for you. There's no clear starting point, right? The best resource to learn PDL, apart from this, because I think this will be a good intro, is the book. We actually recently finished a book that had been started in 2002 or something. And so there's a PDL book. If you just Google that, it should come up, hopefully. If not, you can always find it through the website, which I'll come back to, but I'll show you now anyway. Here's the PDL website, which was recently redone, thank God. And you can, let's see, where is it? We don't even have it. Oh, here it is. Here's a link for the book, over here down in the recent news. And so that is your best place to get started. If after this talk you're like, wait, I don't remember how to do it, that would be a good place. I'll cover more resources later, but that's, all right, let's go ahead and get going. So PDL is basically, it provides two things for Perl. It provides speed, and it provides compact data storage. It actually provides C compact, like C-level data storage. So if you have 100 pieces of information in a Perl array, those are all actually in what are called SVs. And those, they're not huge, but they take up more than the native C data type. Whereas PDL, when you have 100 integers, it takes up the amount of RAM that 100 C ints would take up. And so that's why it's more compact. It's faster because whenever you do operations over a whole bunch of elements in an array, and you're doing a for loop on that, when it turns out that you want to just increment your index on your for loop in Perl, it has to do a bunch of C operations. If you do that in C, it does one thing. It adds to an integer. And so what PDL does is it basically does all of the looping in C code. So it's very fast. And I should say up front that most of this part of the talk is mostly a repeat of what Carl Glasbrook wrote. He wrote an intro kind of like Get Your Feet Wet, and that's the first chapter of the book. So if this doesn't make sense, hopefully Carl's an excellent writer, and you can go back and read the book. And then if you read the book and it all seems familiar, it's because I stole a lot of it. Carl Glasbrook was the original creator of PDL, and he actually used it to analyze some data and publish a paper or a number of papers, and the guy has like an enormous number of citations, so he's like a scientific god. Anyway, here's my first example. So here's the code that produces this figure. What we have here is every script that uses PDL. You don't need these two, of course, but you need to say this. And that pulls in a whole bunch of sub-modules. It's not the most Perlish implementation of handling sub-modules. But it gets the job done. So it pulls in complex number support. It pulls in all of the basic functions like overloading logarithms, sine, cosine, the operation overloading, etc. So for example, it pulls in this function called sine. It puts that in your main namespace. If you didn't want to have that function, you could use light, and then it would not import those functions for you. But you guys aren't probably too worried about this if you're just using PDL to analyze data. So this will pull in the sine function, but that sine function is going to operate on this piddle. By the way, we call them piddles because Perl already took arrays. So we use piddle. It's kind of a pronunciation of this, right? This will produce a bunch of radial values. So you can imagine this is a 200 by 200 matrix, which we're visualizing, and the middle of it is 0. So let me show you what this actually looks like. The middle of the matrix is 0. And then as you go one step out, it's 1. And 2 steps out is 2. But then if you go one step out and up, it's the Euclidean distance. So it's the square root of 2. So this basically measures the distance from the center. And then we can evaluate the sign of that. So let me make that a little bit clearer. So here, this basically shows you've got a 5 by 5 matrix. The middle one is 0, right? You can actually specify that you want, say, the position 3, 4 to be 0, and then every point will be measured from there. This is handy. It's a useful way to generate data. The same is for a sequence. This just produces sequential values, just like, and then you can also do X vals or Y vals or whatever. So these are all different ways of generating data that you may find. I can't believe this. So you all know to turn off your phones, right? Yeah, that's me. All right. We're just going to turn that off. Good. So lots of ways to generate basic data. And that's what I do here. I generate these radial values, and then I evaluate the sign of it. Now, notice this is one Perl function call. This is an overloaded, a second Perl function call. This is a third function. I do 3 Perl operations, and I produce, is that 40,000 pieces of data that I've hammer on, and I produce this plot. So it's very fast. And so one of the things we can start doing immediately with PDL, because it's way cooler than C, is we have all these libraries for loading data and analyzing data. So astronomers like to use this file format called FITS, and there's this awesome picture of the Hubble. You can't see it, by the way, because you actually have to, humans see dark and light in a logarithmic scale. So you actually have to scale it logarithmically, and then you can start to see what's going on here. And this kind of does thresholding. So, oops, Control Enter. So this, can you make this out? This is a spiral galaxy, right? And so what I've done here though is pretty cool, right? Because I took this value, this raw value, and here let's make that a little bit brighter. The raw value from this M51 file, I calculated the maximum, divided that by 500. So these are Perl scalars here, right? But then I added that scalar to every element of M51. And then I took the logarithm of every point. So anytime you specify this function, it does it on every single point in the matrix. Some functions they'll do an operation on a whole row, right? So max does an operation on the whole piddle. And there are ways in which all these different dimensions are specified. But this is pretty cool, because again, this is like, 3 or 4 Perl operations, and it's doing this enormous calculation. Now, what you'll notice, if you look closely, is there's kind of this wavy pattern. So here's darker, here's lighter, here's darker, right? This is manufactured. But it turns out that with normal telescopes, with normal sensors, there's always, each little element, detector element is going to have a different amount of sensitivity. Where you do this, if I remember Carl's writing about this properly, is you have your dome of your telescope, and you orient your telescope at a white part of that dome that's uniformly lit. And then, of course, it should all come back at the same level if everything is properly normalized, right? But they're not. And so you'd get something like this. So you take this raw data that I've already loaded, and then you load this flat field, and then you correct the data by, in this case, because of the way that the instruments work, by dividing. So I would have done subtraction for this sort of stuff. I was doing if I was doing some sort of corrections, but if for Carl's instruments, they would divide, because that's how the sensitivities work. And then all those waves are gone. So this is doing something a little bit different. I mean, you can think of, well, I guess it's more or less the same, except now we're talking about taking one piddle and dividing it by another, right? So again, this is taking the first element of the first piddle and dividing it by the first element of the second, and then going over one and over one and over one. So this is 512 by 512, so that's, what, 250,000 or something, right? 250,000 operations. And this is live, by the way. Like, I can change these, right? So these operations are happening as I talk. So it's very quick. All right. So I've described, yeah. Oh, so this thing, yeah, this is a little IDE I wrote using Prima. And I could talk quite a bit about that. This is what I would like to convince MATLAB users to come over to Perl, because look, I wrote this awesome IDE, but I haven't been able to market this yet. It's on CPAN, but it's still maturing. But yeah, so yeah. Anyway, although if you think it's cool, you should come to my plotting talk, because I wrote a plotting library. All right, enough. When you want to do these fast operations, right, that's great when I say, okay, calculate the sum on this matrix. But what if you want to calculate the sum on only a portion of the matrix, right? If this is C code, well, you're writing for loops. So you would have, loop over x, loop over y, and then if the location is where you want it, include that in the sum. You'd have an if, right? But imagine doing that in Perl. We'd have two for loops and an if statement. And so each of these for loops, compared to a C, for loop is very slow, and then each condition is really slow. The way that you solve this in PDL, and it's a very general and very powerful solution, is you take a slice of your data, and then you hand that slice off to these operations. So the way you specify a slice is you have to specify a mask. So PDL has overloaded the comparison operators. So in this case, I'm using the rvals thing, which I've already shown you what that is, and then I say, okay, wherever the radius is less than 70, that's 1. And wherever it's greater than 70, that's 0. And that's what you have plotted here. Right? So this is actually a 512 by 512 matrix. That happens to be 0 out here and 1 in here. Right? So if I change this, then it gets bigger. Right? Now I can use that as a mask in what's called where. So this says, set all the values of center where the radius is greater than 250 to 0. Now think about this. How many lines of code this would be in C to do this? All right. This is one reason why PDL is really nice. Now, you really can't quite see that, can you? Let's change this contrast. That's a bit higher. Okay. So hopefully you can see there's this little circular edge, right? And then if I change this radius to, say, 50, then I'm only looking at the center, right? Now, what I've done here is I've set values to 0. And you'll notice this is not equals. It's not equals because we weren't clever enough to tie the returned object to overload the assignment. Anyway, normally you'd think, if I have b.c, that's concatenation. Right? And if I have some variable that, you'd think, oh, this is going to tack C onto it. Well, there's no use for this operation in PDL, and we needed to have a simple way to do assignment. So we overloaded that. If you start using PDL, you will make this mistake. And when I wrote this slide, I made this mistake where it just said this. And if you do that, it doesn't do anything. And you'll be scratching your head like, wait, I thought I signed it to 0. Well, you have to actually put the dot equals in order to actually make it 0. But the cool thing is that now we have this language to specify regions. In this case, I'm using where. And you notice where is not... It could look for values, for example, where the center, let's say where the center is less than M50, yeah, center max over 2. And then this will assign it to 0, and then we'll get, I have no idea what this will do. Oh. Oh, it went off the side of the screen. But, okay, so because the max is so much higher than the rest of the data, right? So if I take the max over 2, it doesn't buy me much. But the point is that you can put whatever mask in here you want in this where statement. You can also use regular sort of array subscripting, except that the PDL folks didn't like using a function call. We wanted to make it even more compact. So what you would normally say if you didn't use nice slice is you'd say my slice is M51C slice 200, 400, 150 to 350. But they kind of got tired of writing all this. And so nice slice is a source filter. It's a very good source filter. And it's one of the few situations where you actually want a source filter. Because I do slicing often enough that I want a special piece of syntax for it. Right? And so actually having something like this is useful to make my code more concise. But we actually had someone who had something that looked like this in a SQL query. And he's like, what the hell? And so Chris Marshall, who's the pumpkin, he actually modified nice slice so that it used, I don't remember. I don't remember what it was. But, there's like the standard way to figure out when something's quoted, and you don't hammer on that when it's quoted. You only hammer on stuff that... Anyway, so he did this, and now it doesn't affect this guy's SQL queries. Like, we've tried to make it really good so it doesn't have too many nasty side effects. Anyway, if you do that, then I can take a little subslice, a rectangular subslice. And so these are the different ways of getting at data. All right. So this is the takeaway point of PDL. If you're going to use PDL effectively, you want to minimize your Perl loops and maximize operations on slices, even if they're complex slices. There are a couple of situations where this is not always best. There are a lot of situations where the code looks extremely obfuscated when you have a complex slice. Sometimes it's better to optimize for readability, right? But if you want to have things that are fast, you do it by performing slices, not doing for loops. If you write a for loop, that should be like the indication, I'm not doing this right. And then if you're not sure, then you send an email to the mailing list. And you're like, how can I make this better? All right. So something that I'm about to break this rule on the next slide. But what I wanted to start doing was, let's actually do some analysis on this M51. So what I'm going to start doing is analyzing concentric rings. So if we look at this rather large concentric ring, right, it has these values, right? But I could look at just this one and say, oh, that's kind of bright, right? The center, of course, is quite bright. And so how does the brightness decrease as you move away from the center? The center of the galaxy is going to be the brightest part, right? So what this will do is it will, actually, if I uncommented this, we could see what the brightness would be, because it would tell us. There it is, 463,122. And Carl has a section in the book where he actually figures out what the units are on that. I'm not going to go through that, because I'm not an astronomer. But, okay, so let's say we change this from 40 to 50. Now it's 52,000, or 523,000. That's bigger, right? Which is kind of weird, because it's further from the center. But it has a larger area. So it kind of makes sense. We're measuring brightness, not luminosity. So instead of doing this for every single ring and looking at the numbers, we can just make a plot. And so that's what this figure shows. Here is your distance from the center along the x, and along the y is the brightness. And that's the integrated brightness over the entire area, right? And here you can see I've already broken my rule. I have a for loop. And the reason I have a for loop is because you can actually perform this using what's called the range function. But it's already kind of complicated enough as it is that I didn't want to use range, and I'm not, well, we won't go into that. Anyway, what this does is it says, okay, take the inner radius minus 5, where the inner radius is Oh, sorry. Let me start at the top. Okay, so we create a 37-element PIDL. Runs from 0 to 36. And then we multiply by 10. So again, the figure is 512 by 512, so roughly 380 is about where the edge of where I care to look. And so this will be the center of each concentric ring. And then I'm going to sum all of the values of M51 between that center line minus 5 and the center line plus 5, because they're 10 radios. You know, the radius of each, the thickness is 10 centimeters. So this combines two masks using the single ampersand. If you have two ampersands, PDL croaks. It overloads this to croak, because you can't use a PIDL in a logic operation unless it's a single element PIDL. But a single ampersand will just do a bitwise mask combination. You can also do an OR, and you might be able to do something else. But these are the only ones that you should ever sanely use. Okay, so it then takes the slice, it performs the sum, and it pushes that onto this regular Perl array called brightness, because Perl arrays are much more flexible at changing their shape than PDL arrays. And then it builds an actual PDL array and plots it. So what we see here, of course, is that the brightness peaks. And I already said that's because the area gets bigger, right? So we can correct for that by dividing by the area of a ring. So this is so now what I've done is I've loaded PDL constants, which gives you pi and e and maybe one other. And it's not very big yet, but if you can think of good constants, we'll add them. And so then it basically divides the brightness by this, you know, the area. And now we can say it drops off, which is exactly what we expected. And in fact, if we look at this with logarithmic scaling, we see something very interesting, if you know what you're looking for. This looks like an inverted parabola right here. So because this is logarithmic scaling, that means this is basically like a Gaussian. It's e to the minus x squared. Okay, that's kind of a standard distribution, right? Except this part right here. And that's because the center of a galaxy has slightly, it actually has a different signature than the arms of a spiral galaxy. And now we're going to the very edge of my cosmology class where I'm getting very fuzzy. But so the reason is because the center of a galaxy, I believe, is like a clump, whereas the rest of the galaxy is kind of flat. And so the density of stars is actually higher, and it shouldn't follow the same distribution as the rest of the galaxy. So that's kind of what we're seeing here. And so these are, I mean, if you actually were to cut out all of my yakking and just look at the code, I mean, this is probably 150 lines of code to get to this point where we can already start looking at the luminosity distribution of a galaxy. Right? That's the amount of code you have to write to do some cool stuff in using PDL. Now, imagine doing this in C. Not quite so fun. Wait a second. That skipped a jump. Oh. Okay, sorry. There we are. So the last thing I wanted to do was look at a single star. So this is a particular region of the original M51 image that's on a particularly bright star. And one of the questions you can ask is, like, how does this so we've already seen what the luminosity of the galaxy itself does. It's exponential with that little extra bump in the middle, right? But a star shouldn't have that. It should be relatively standard. And so what we can do then is kind of look at how the intensities drop off as we move from the center. So that's what this figure kind of shows you. It drops off. That's kind of what we expected to see. And you can kind of convince yourself it looks almost like a Gaussian, maybe. Anyway, let's actually fit it to a Gaussian, because the functionality for that exists. So what we'll do is we load PDL fit Gaussian, and then oh shoot, sorry, I haven't practiced this very well, so bear with me. And if you have questions, please ask them, because you will learn quite a bit more if you ask questions, especially since I'm not very well rehearsed. You can't screw me up by asking a question, but you can learn more. All right. what these functions do is they take what was a two-dimensional matrix, right, and they rearrange it so that it's a one-dimensional line. Which you say, well, why would you do that? You would do that if you're actually, if the function that you're about to use expects a vector, not a matrix. Okay, and so that's what the Gaussian fitting function expects. What was that? Oh, sorry. That's what we have to do in order to do the fitting. For the plotting, it doesn't matter. The plotting can take whatever. But for the fitting, we have to do this. And this is a very cheap operation. All it does, so in C, all of the data is stored in consecutive bits. And then it's just a question of what your indexes mean in terms of finding the offset. So this is actually extremely cheap. It doesn't even copy the data. It just kind of makes a mental note and says, okay, when you actually ask for this location, I'm going to do the offset calculation differently because you've decided to get rid of the two dimensions. So that means we can send that to this PDL fit Gaussian routine called fitgauss1dr because it's a radial Gaussian. That's something I don't really quite get, but astronomers use this apparently. So this prints the peak height of the Gaussian, the full width half maximum, and the background. And if we actually look at the printout, no, that didn't run. All right, well, let's run it. So the peak up here is this value, 19202. The full width half maximum is basically if you were to find the half, like from here to here, there's a certain y extent, right? So go halfway in between, that's basically here, and this is the half width. The full width gives you the full width of the actual Gaussian. That's useful because there's some distributions that are shaped like a bell curve, but they don't have or the standard deviation is not well defined on it, but you can define a full width half maximum as a meaningful thing. So scientists a lot of times refer to the full width half maximum of a distribution. And then finally the background is, this doesn't actually go to 0, right? So it shows the background is 94. So this curve looks pretty good, and this would give us a pretty good idea of what this star is doing. And I'll show you if we actually do logarithmic scaling in y, then it's good except for this little corner here where it drops off not quite as fast as a Gaussian would. But it's still a pretty good fit, and this allows us to do science. Like this is, I mean, this is good enough that I could actually use this to do calculations on this star and get properties on it if I were an astronomer, which I'm not. I do complex systems research and time series analysis. Hopefully we'll get to that. So, whoops. All right. So now I'm going to pause and kind of shift gears. That's been the introduction to PDL, how to use it, like kind of the flavor for it. And now what I want to do is give you guys an idea of where to find information if you really wanted to start using this in your scripts. So before I do that, are there any questions you guys had about the stuff that I've gone over yet? Or is there anything you just want to ask at this point? Yeah?
Does it only work with numeric data and matrices?
Okay, so the question was, for everyone recording, does it only work with numeric data and with matrices? So the short answer is yes. It does. For example, I do some stuff with complex networks, and there's pretty much no efficient way to use standard PDL to efficiently encode complex networks. You can use an array, but it would have to be a sparse array, and PDL itself does not have sparse array support. There is a sparse array library, but if you pretty much have to put your calculation into some sort of a matrix, a vector, a matrix sort of a notion. And then, is it all numeric? Yes, it's numeric. I occasionally will create PDL routines that set that use a long as a data type, and it actually stores pointers to structs. And then I write routines that know how to operate on all those structs. But I'm a core hacker, so I know how to do this. But standard PDL doesn't yet have support for arbitrary data types. It is something we'd like to do, but there are many things we'd like to do. So, yeah. Were there any other questions? Okay. So This is supposed to say recommendations and suggestions and something over here, but I don't know what it is. So there's the basic places to get information is pdl.perl.org. This is a good launch point. This can tell you how to get it. You can install it through CPAN, download it for your flavor of Linux or Windows or whatever. You can do the documentation. Help, I think, basically takes you to the mailing lists. The primary way in which PDL operates, like if you have a question or if you have a developer idea, then you should go to the mailing list and you should say, hey, I have this question. There's two of them. I guess I can just click on this. There's the users list called PerlDL at jach.hawaii.edu, but it's not showing. And then there's the actual developers list. Most of you guys will be interested in in this one. There's also irc.perl.org. There's a PDL channel, which I try to be on regularly. And if anyone has a question, I try to answer it. It's kind of been quiet lately, but if you guys have questions, that would be a place to bug me. Now, there are a lot of modules that are distributed with PDL. It's kind of a kitchen sink distribution, but it's a selective kitchen sink distribution. It's both great and kind of irritating at the same time. So one of the most useful documents, apart from the PDL book, is this thing that I put together called PDL course. This will say, okay, you're a beginner. Why don't we start with reading these basic documents? Read them. You'll have a pretty good idea of what PDL is about. This covers the nice slice syntax, which you've already seen, right? And then it covers, don't read the entire thing from PDL core, but you should be acquainted with it. So this would, if you want to actually start learning about the different things that PDL has to offer, I don't have time to go through all of them in this talk, or if I did, you'd fall asleep because it would be just a listing. But this would kind of take you through it. I do want to point out a couple of things, though, from this. There's the PDL shell, which is actually a command line shell. It's a running val print loop. And so I can say print sequence 20, and it'll do that. I can do calculations. It's basically a running val print loop with PDL automatically loaded and nice slice are automatically loaded. So this allows you to do calculations from here. People will do calculations and do plots from this. I always write scripts, but some people like to have this sort of functionality. So that's good and important to know if that's how you like to function. There are many different input-output formats. The PDL knows to read, or if your library is on your system, then it can actually install the hooks for that, and that's all summarized in this one. One of the cool things about PDL, something that makes it different from any other library that I know of, is it actually has support for bad values. Now, this is not the IEEE not a number. That is not a number. These are bad values. So, for example, going back to this telescope issue, if you know you have a detector that is bad, you can actually mark like a pixel. You can mark that as bad. And that point will not be taken into account. Well, the value there will just basically be tossed out. And instead of having a 512 by 512, you got a 512 by 512 minus 1. And if you say, how many elements do I have? I think it tells you 512 by 512. But if you say, how many good values do I have? It's 512 by 512 minus 1. You can do all the statistics, and they automatically take bad values into account and basically ignore them. There are all these cool aspects that you can use bad values for. Another thing is the plotting libraries, some of the plotting libraries take these into account and insert line breaks when you have a bad value. It's really cool, and it's not available in standard C libraries. There's Fourier transforms. There's some support for complex numbers. There's wrappers for parts of GSL, though not all of it. And this is a really cool thing, which there's a guy who's been on the PDL list for years. And he didn't know about this. And he's like, I wish I knew about this when I was working on my dissertation. And the guy's been a professor. So what this will do is it'll, if you wanted to analyze, say, 50 images, 50 of these galaxy images, and maybe it's a movie, so they're sequential. Every night they're a different picture, right? So you want to know how the luminosity changes or something. You would just normally do a for loop over a glob, right? And you just go through that. Well, disk cache will take a glob or some sort of a string expression, whatever. I actually don't remember the exact details, but it basically will get a bunch of file names, and then it will return a tied array. So then you can just say, okay, give me the third file, and it'll return a PIDL. And it'll cache the last 10 files that you did. So you can actually access them in random order rather than accessing them sequentially. It's useful and it's most efficient when it's sequential, and it makes for really concise code. But it also makes it much easier to do random access. All right, image manipulation. I won't go in too much into that. And then the last thing I want to mention is that this PDL doc, this is actually a command line tool. PDL has, we have our own little specialized things we do with pod that kind of indicates sections of the pod that are helpful. And for example, if you wanted to look at the documentation for clump, you would say PDL doc, clump. And rather than giving you PDL core, where like all the documentation for PDL core, it just gives you the section that pertains to clump. It's very useful when like, wait, how does rvals work? So let me show you rvals. And this is the documentation for it. And most of these functions have working examples, so that way you can just copy and paste this and start playing with it immediately. So rvalues, I hope I said this, that it actually it takes options like specifying the center. So instead of taking it from the center of the matrix, you can say, I want the rvals to assume the center is over here, which is useful because most of the time, the center of your galaxy is not at the center of your image. You have to calculate where the center is, and then you do r values from there, right? So, but I digress. If ever you can think, oh, I think there's this function, what's the documentation for it? Use PDL doc. Or if you're in the PDL shell, you use a single question mark clump, and it brings it up. And if you know there's something that involves, say, the cosine, but you can't remember what it's called, you can do this double question mark, which searches through all the text of all the different functions. And this couldn't actually find the word cosine, because no one ever typed out the word cosine. But if we said complex, then it brings up all the different functions that discuss complex something or other. So those are useful resources for actually finding information and getting stuff done. Okay, that's all I have to say about that part. I want to also cover a couple of important modules. Just about anything you see on CPAN, there's not an enormous ecosystem of PDL modules, but there's actually more than I gave CPAN credit for. Part of that is because this guy, Mukau, just started loading a whole bunch of PDL modules that he's written. And so those are now on the CPAN. So this is the sparse matrix support that I had mentioned before. If you're doing, say, complex network calculations and you need a sparse matrix, this does that. I've never used it, but I know that it does some deep magic, so I think it actually works well. It's not just some silly Perl level thing, which is terribly inefficient. I think it's actually pretty good. PDL util is going to be something a midway point between something that actually gets to core. We haven't quite figured out how to use that yet, but that's being administered by Joel Berger. PDL stats is the next talk. Maggie Zhang, who's right here, will. She's not going to raise her hand. She's wrapped up the GSL statistics functions, right? And
just one GSX module. The rest is just native PDL.
Okay. Oh, so there's a lot of native PDL stuff in there too. So, yeah, basically what she said is that there's. I mean, the next talk will be about this, but it's some GSL stuff and it's some just straight PDL hard-coded functions to do statistical calculations. So if you find yourself doing statistics, you'll want to use this module. Adam Kennedy wrote something to interface PDL with OR Lite. There's the singular value decomposition library. A number of other cool things. If you know what these are, they're there. You should use them. There's one that I wanted to get to on the next page. Oh, PDL audio actually allows you to send, do manipulation of a PDL, a sound wave, and then send it to hardware. It actually can go through your speakers. If I had known this years ago, I would have used it, but I didn't know it did that. I only learned that a few months ago. So that gives you another way to interact with your data, right? Plotting, of course, is a very obvious way to interact with your data and see it. PDL audio gives you a way to actually hear it. I also wanted to point out this plugin for Padre, which highlights all the PDL functions, main functions, which can be very helpful if you use Padre. I do. And then 2 new plotting libraries. I'm going to discuss PDL Graphics Prima, but there's also PDL Graphics GNU Plot. There are two others that actually distribute with PDL. One's based on a Fortran library called pgplot, and one's based on a C library called plplot. So these are all the different ways to visualize data. Those two are distributed with these two over here are obviously not part of PDL. And then if you ever do any color manipulations, Maggie has also written a color space manipulation package, which does all kinds of different color representations. And finally, if you do parallel calculations on a cluster, this works. It does not install from CPAN. I had to manipulate the makefile myself to get it to compile, but I got it to compile on my cluster. And then you can write Perl scripts that do high-performance computing on a compute cluster using PDL. So that, I hope, is kind of the broad spectrum. Now you know about everything you need to know, I would hope, to get started to find resources for everything. So I have about 10 minutes, and I wanted to actually show you a real calculation that I've done using PDL. Most of this was data analysis, but that's kind of what PDL is. My mom went to the hospital about a month ago because she's diabetic and her blood sugar went sky high, and your body does all kinds of weird things when that happens, so we all got scared. She was fine, and she recovered just fine, because once you got that under control, like, your body goes right back to normal. But we were curious, like, okay, Mom, you need to tell us when your blood sugar is high, right? And she's like, but you don't understand, the blood sugar spikes. And so I said, okay, well, let's look at the data. Let's actually see what your blood sugar does, so we can define a useful protocol, so you know when to tell me and my sisters that things might be going wrong, right? And so this is, I took my mom's logbook from September 1st to April 1st. It had 925 pieces of information. I entered it by hand. It was very tedious. But this is the time series, and so this indicates the number of the day. So day 0 is August 22nd. So day 40 is September 1st, day 70 is October 1st, etc. So you can actually zoom in, and on an individual, she takes about 4 or 5 readings a day. So, day 75 to day 76, she had a reading there, So you can see they're kind of all over the place. And a normal human wants to be between about here and here, 80 to 100. Diabetics have a very hard time doing this, right? Because their body doesn't control their insulin. They have to, well, if they're, I don't remember which is which. She doesn't produce any insulin, so she has to take shots, so she has to use a pump or whatever. And so a diabetic's blood sugar goes all over the place. And this is not atypical, actually. And so, if we were saying, oh, maybe when it's over 250 you should contact us. But this spike, well over 250, that happens it's not uncommon for that sort of, spike to happen. Now, of course, I'm not anywhere near another spike. But, yeah, so you can see, she would have been calling us 2 or 3 times a day in this region, right? I think this is a time when she was kind of stressed out, so she had higher measurements. But so, what does this look like? What does the distribution of these look like? These are the actual readings, and it's not a Gaussian. This is actually kind of has a little heavy tail, right? And so we could set a cutoff, and maybe that would work, maybe it wouldn't. But what I'm doing here is I'm trying to. Sorry, let me back up and try to be more pedagogical. So, in this case, I wrote a little module which reads a CSV file for me. But what this does is it regularizes the dates. All the dates are. Oh, don't worry about this. This just moves the dates. It doesn't really matter. But what I can do is I can specify, okay, let's see what happened in the first 10 days. Like, how often did you have a reading above 300 or around 100 or whatever? And I can change that here if I wanted to. And then you can see it's quite a bit more sparse. But that's basically what this half does is it says, I have this whole time series, but let's just look at the first bit or the second chunk or the third chunk. And this is doing what I've already shown you, right? It's this slice using where, and it applies this mask, so where the dates run from start day to stop day, right? And then it just plots a histogram. Now, who here is familiar with reading histograms? Okay, yeah, so it's sort of like, it's basically a distribution or a representation of the likelihood. So you can see my mom is most likely to have readings around 90, right? But then there's a fairly decent likelihood that she'll have a reading around 200, right? So that's what this is supposed to visualize, is sort of the likelihood. All right. So one question that I was curious about is, it seemed like she was doing really well earlier in the year, and then it got worse. So if we start from, say, day 100, will it still have this shape, or maybe the peak will have shifted? And it's more or less the same shape. If you look at, say, 150, maybe it's a little bit higher. But it turns out that, for the most part, her behavior has been consistent, which is good. That means we can actually establish a policy that will apply. This is actually her readings throughout the day. So there was one day where she had a reading at 3 o'clock, way down here, or she had a reading at, 4, 5, 6, 6:30 that was really low. And so, but what you can see here is that there's no time where she's obviously consistently low or consistently high, except the mornings. In the morning, she tends to be right around here. But, you might say, oh, well, okay, if you have a reading above 200 and it's just after lunch, that's okay, because everything is above 200. But that's not the case, right? They're kind of distributed all over the place. This turned out to be a really hard problem. I wanted to find something predictive. Like, Mom, maybe the day before you have these terrible spikes, it's because, we can detect it because you have high fluctuations or something. And I did all these analyses using PDL, and it turned out I couldn't come up with anything, which is very frustrating. But at least I knew I couldn't come up with anything. At the end of the day, we ended up saying, okay, if you do this, then do that, and then if it still is a problem, call us. We came up with something, but we couldn't predict. And that was frustrating, but at the same time, it was nice to actually be able to come up with that conclusion through this analysis. And there's one more thing I wanted to show. Yeah, so if we actually look at the distribution at different times of day, so this is from midnight to 10 o'clock in the morning, it's peaked around 100. If we look from 10 o'clock to 2 o'clock, it kind of moves up a little bit, right? But more or less, all the shapes, except for the morning, are kind of peaked around the same time. So there wasn't a whole lot we could do with this information. It would have been nice if it was typical that she was high on one time and not another, but that wasn't the case. Okay, so let me finish by saying there's all kinds of ways to learn PDL. There's this talk. There's the book. If you know MATLAB, if you know Scilab, there's actually been some tutorials. Actually, that may be PDL tutorial MATLAB. I'm not sure. But if you go to the website, it has links to these tutorials. There's the course that I already showed you. There's a kind of a hand-curated list of the modules, which is more by topic. So if you know you want to do visualization, like if you want to do 3D plotting, there's a module that does that using OpenGL. So if you know the general topic, you could go into modules. PDL index is auto-generated, so you can look at PDL index on your machine, and it'll give you the list of modules and their documentation that's on your machine. So if you don't have SlayTech, because you don't have a Fortran compiler, then it won't show you the SlayTech bindings, right? Which this is handy when you need to actually see what's on your machine. If you need help, if you're interested in this, you should sign on to perldl@jac.hawaii.edu. That's also, you can find a link to that from the main PDL page under the help link. This is the best place to get help. It's better than Stack Overflow because there aren't enough people asking questions. It's better than Perl Monks because no one from the PDL community monitors Perl Monks. This is the place to get answers. If you want an immediate question or answer to a question, you might be able to find me on the PDL channel on irc.perl.org. There are a number of people who are on there with varying levels of expertise, so you can always try. And these are the important names to know. Chris Marshall does all the release management, and he's working on 64-bit offset support, so we can have enormous PIDLs. Carl Glasgow created it. These two guys are geniuses, but they've moved on to other things, and they've left us with this brilliant, really hard-to-understand software. And Craig DeForest is one of the guys who gets it, and then I'm sure there are some others as well. And Maggie, who's going to be talking next, is also an awesome contributor to kind of larger PDL community as well. So that's all I have to say. Thank you very much, and I'll take any questions as well. Thank you. Anything? Yeah.
So I'm sure you're going to cover it in your next session, but what's logic theories?
Yeah. Yeah, so Prima is kind of like TK. Yeah, oh, sorry, yeah. So the question was, what is the software I'm using? So there's a couple answers to that question.
So I know Prima, I'm just wondering which Perl model is driving that.
Yeah, so, anyway, so those of you who don't know, Prima is like TK, except that it's written specifically for Perl, and you can install it straight off of CPAN. It's awesome. Well, you can do the TK too, but I digress. Anyway, I found Prima, and its internals are beautiful, and so I wrote a PDL module that does all the drawing operations with PDL operations. Then I wrote a plotting library on top of that. So all of the plots that you've seen use the plotting library I wrote. This thing is actually just a Prima application, which is just a REPL that I wrote so I could play with my data more easily with the GUI kind of a toolkit thing. So I wrote this. This is available on CPAN under app Prima REPL. And then the plotting library is PDL graphics Prima. So if you're interested in either of those, that's where you can find them. Yeah. All right, awesome. So if you know people who use MATLAB, tell them to do this. And give them, I didn't give out my email address, but you can find me. Have them contact me if they have questions or join the mailing list or whatever. And I hope it works out. All right, great, thanks.